There we go. So can you see that, or do I need to? Yeah. I can. Then it's easier to see, right? Yeah. Excuse me. Yeah. So, yeah, Audric is in practice, I think, at the moment, so he's not able to Zoom with us today. But thanks for asking me about some of the homework earlier. And it's interesting to notice, that the book has a different definition of a vector space than I typically give in my classes. And it's probably a better definition because it's, in the sense that it's, I think, more logically minimal. But, so what that means is everything I state for a definition ends up being part of the derived consequences of their definition, and that's why there's those homework problems. So, okay, so here we are, section 1.3, which is on normed spaces. So I'm hoping to get a ways into this. As I told you earlier, I do feel a bit guilty for not supplying proofs of Holder and Minkowski's inequality. I guess one of those is a homework problem, so I shouldn't feel too bad. But and it is in the book, but I did want to at least, I'm hoping to add that to the playlist later. But anyway, so here it is. Definition. A function x maps to norm x from E to R is called a norm if it satisfies following conditions. So condition A, norm of x equals to 0 implies x equals to 0. And B, the norm of a scalar lambda times x is equal to the absolute value of the scalar times the length, times the norm of the vector again, for every x in E and lambda in the field. Now that field is, I think, for us either going to be the reals or the complexes, right? But I'm sure you can I'm sure you could do some of these things over a finite field if you were so inclined, or perhaps the t-adic field. I don't know. So absolute value of x plus, norm of x plus y is less than or equal to norm of x plus norm of y. And you'll forgive me, I will slip into calling the norm the length, because I think of norm as a vector length in the abstract sense of vector. It's the generalization of, spatial length to arbitrary mathematical objects. So this is the definition. And if you look at my notes on anything, you'll notice that, like in my notes, I assume that the norm is non-negative. He doesn't, but he proves it. So this is kind of the same issue. I was just talking to you about the first couple homework problems in chapter 1. Kind of the same issue, And so let's go through his little argument here. He says, okay, so 0 is, if 0 is equal to, 0 is equal to the norm of 0. How do you know that?
Well, it's B for every x and E and lambda and that. So lambda is...
Okay, so yeah, this is from B with lambda equals to 0, right? Okay, yeah. Okay, and then that is equal to, where was I? Of course, 0 we can trade for x minus x, right? Which then is less than or equal to norm of x plus the norm of minus x, right? Which then, again, by B, we can, a corollary to B is that the norm of, you can easily get lemma, right? The norm of minus x is the norm of x. Just take lambda equals to minus 1, you get that, right? Because you can also prove that -1 times a vector is in fact the negative of the vector. If we're at this level of minutia and quibbling over the definitions, we can get into it if you want, but actually I don't want to do that here. So this is twice the norm of x, and so what does that show us? That shows us that 0 is below, well, it shows us that the norm of x is larger than 0, right? It could be 0, but it doesn't have to be. It can't be negative is the main thing, right? So the norm is actually a mapping, like you could replace this, right, with 0 to infinity if you wanted to make a different definition, which was kind of more heavy-handed. Like I said, it's kind of, some definitions are more pedagogical in the sense that the definition tries to emphasize like what the properties of the object are that you're defining and sacrifices logical minimalism for, communicating what is this thing. It's, I mean, whatever. You can go either way. Now let's see, another calculation we should go through. So next, observe. Check this out. So if we start with the norm of x, right? Then we can add and subtract y to that. So this is going to be the norm of x minus y plus y. Because I just added 0, right? Then apply the triangle inequality. Oh, my bad. I wanted to keep those together. Minus y, norm of y. And then that gets us what? That gets us that the norm of x minus the norm of y is less than or equal to the norm of x minus y. And let's see here. And then, so I suppose, and this is where I got to in my class preparation, sadly, today. I was hoping to have more prepared, like beforehand, but we'll work it out together. It'll be fine. It'll slow me down. It's good. Now, if this is positive, right? So either this is positive or this is negative, right? So if it's positive, in other words, if norm of x minus the norm of y is greater than or equal to 0, then what? Then the absolute value of norm of x minus the norm of y is equal to, norm of x minus norm of y, right? All right. Number 1. Number 2, if the norm of x minus the norm of y is less than or equal to 0, then what do we have? The absolute value of the norm of x minus the norm of y is equal to, absolute value of norm of y minus the norm of x, right? So what I'm trying to see right now, I'm trying to put absolute value here.
Yeah.
So in case 1, we're done. So let's labor here in case 2 for just a second. So I've got norm of x minus norm of y is less than or equal to norm of x minus y. Great. That was just what we had already, right? Then how can I go from here to that? Oh.
If you had the norm of x minus y is less than or equal to norm of y plus the norm of x. No, that's the wrong way. Sorry.
I mean, maybe it's just that, so I'm not sure if it's directly from here, or my other thought was maybe I just have to do the same trick again, but instead of letting y play the role it did, let x play the role that y plays. Does that make, I don't know if that makes sense. Like I can also get, all right, we're going to spend about 2 minutes on this, and if it doesn't work out for us, then we're going to we're going to bail. So, yeah. So norm, this is, y minus x plus x, right? Which is less than or equal to norm of y minus x plus the norm of x, right? But of course, this is equal to norm of x minus y plus the norm of x, which gives us that the norm of y minus the norm of x is less than or equal to the norm of x minus y. So this is also equal, and we're in case 2. I mean, this calculation does not, this calculation is true in cases 1 or 2, but we can apply it in case 2. So like this, this is true, right? And let me just do it down here. I'll do it over here. So thus, in case 2, the absolute value of, norm of x minus norm of y is less than or equal to the norm of x minus y. So whether we're in case 1 or case 2, and that exhausts the cases, so we have then, lemma, proposition, whatever you want to call it, that the absolute value of the norm of x minus the norm of y is less than or equal to the norm of x minus y, right? And of course, the triangle inequality equally well gives us that this is less than or equal to the norm of x plus the norm of y, right? So, as a sort of just, whenever I face sort of abstract bounding problems, it's useful to keep this family of ideas in mind, because it gives us ways to make things small or large, right? Like if you're trying to, if you have something where you have like the norm of a difference in a denominator, and you want to make the fraction larger, if you can make the denominator smaller, that's where this would often come into play, is like if you're dealing with a fraction and something like that. But okay, enough. enough. Let's go on. So examples. So this is his example 1.3.2. I should probably get in the habit of using the book's numbering just for the sake of reference. So the norm of z is the square root of the norm of z1 squared plus, absolute value, all the way out to zn squared. So this is for, the norm for complex n space, right? And this is called the Euclidean norm. There are other choices. All right. There's also the, I usually call it the one norm. He doesn't actually give it a name, I guess, but this one. So it's just the sum of the moduli. That's a norm. I mean, I'll just give it a name, one norm. And then there's also what I'll often call the soup norm. So you can also, and of course we need different notation for these to be careful, yeah? So the max of the modulus of the first component all the way out to the modulus of the nth component. Right, that you can prove that that's a norm. I mean, I'll call it just the soup norm, to give it a name. And I usually put I usually put an infinity here, and I put a 1 here, and by default we'll use the Euclidean norm, but if you wanted to give it a notation, a sub 2 is kind of the most natural thing to put there for the Euclidean norm. And that actually ties into that larger discussion of the LP spaces that we were talking about. But, okay, so there's example 1.32. And it's straightforward to prove that those are norms. You can see that they're, I mean, let's just look at the, let's look at axiom B. What would happen if you like multiply z by a scalar lambda? See, what happens is when you multiply by the scalar lambda, it multiplies every component by lambda. And so like out here, you're going to get a modulus lambda squared, right? Yeah. You factor it out, then you get the square root of the modulus of lambda squared, which just pulls out modulus of lambda. And the same thing happens in the other cases.
I have a quick question.
Sure.
For the max analysis, is max just used for supremum as well, or is there a difference between the supremum and maximum?
There is a difference between the supremum and maximum. Supremum is defined more carefully. Maximum is what it sounds like.
Right. Is maximum
So,
the biggest element?
Yeah, maximum is the biggest element.
Right.
I think I'll actually need to use supremum for something soon, so we'll get. So his example, my point is it's easy to check that those are norms, right? He says, let omega be a closed bounded subset of Rn. What's that mean? Omega, subset of Rn, closed and bounded. So let me not write too much, just kind of use words. To say it's closed means that its complement is open. Which means that if you delete omega from the space, then every point in that remaining space, you can fit a ball around it, which is in that deleted space. Then bounded just means that you can find a sphere sufficiently large to encapsulate the object. So it is what it sounds like, I suppose. And although maybe this book just used maximum for, well, closed and bounded. Oh, yes. I think this would be by the extreme value theorem this exists. The function, say the norm of the function, he says max x an element of omega, absolute value of f of x. See, he says this defines a norm on C omega. Like almost all the things I'm not proving here make good homework problems, you know. Maybe not good homework problems. Easy, uninteresting homework problems might be the better thing to say, but yeah. So remember, that was continuous functions. So there's a theorem that if you have a continuous function on a closed bounded set, it attains a maximum value, if I remember right. Yeah, because closed and bounded implies compact in Rn. And we have a theorem that on the continuous image of a compact set, it attains a maximum and a minimum. So like there's actually some point on omega that when you plug it into the function, it makes this as big as it can be. Because if you have a continuous function, all right, and you take the absolute value of a continuous function, you again have a continuous function. So like the composition of absolute value with the continuous function is itself a continuous function, and then you're looking at that continuous function on a compact set, which means it has a max, which means that that's at least well defined. And then you can sort through the other things, like if you multiply by a number, you know, the maximum is going to get multiplied by the number, and also like the triangle inequality is going to work out. Why? Because the triangle inequality is true for absolute value, and so that's going to play together with the maximum concept to give you triangle inequality for the function norm. That's what we call hand waving. Notice the motion. Let's see here. So example 1.34. Here we have z equal to zn in the LP space, all right? And he points out that the norm of z equal to, I'll use this notation, the pth root of the series formed by summing the sequence n equals 1 to infinity, norm of z n to the power b he says that's a norm on LP for any is norm any P greater than or equal to 1. Yeah. You notice that you're not really talking about just one norm. I mean, you're talking about a whole family of spaces, right? So, I don't know. You can start asking weird questions, right? Like, if you have something that's like P2 summable, is it also P3 summable? Or what if you have a P3 summable sequence, is it P2 summable? I don't know the answers to these questions, I'm just asking them. I'm pretty I have a suspicion that the way it works is like, well, actually, let me not speculate on that. I don't know. I think that's a question we could ask. All right. So anyway, now that we have some examples, the definition, all right, is a vector space with a norm is a normed space. And a lot of times, some authors will call this an NLS for normed linear space. Because a vector space is sometimes called a linear space for obvious reasons, right? Like, because it's a space where linearity lives, you know? And he mentions in example 1.34 that Minkowski's inequality is the triangle inequality for that norm. Because, well, let me not write it out, but the Minkowski's inequality is literally the triangle inequality for that norm, yeah. And now he says, okay, so it's possible to define different norms on the same vector space, right? So to define a normed linear space, we have to state not just the vector space, but not just the set and the vector addition, but also the norm. See, because for a given vector space, we could define multiple different norms, like we just did in some of these examples, right? Like Cn, we had these 3 norms. I mean, you could add to this basically that. If you just take this example and you think about not having it go on forever, but just truncating it, you know, if you just truncate it, you basically have Cn. You can think about Cn as sort of the truncation of LP, if you think about LP as complex. And so in that sense, that's part of the reason I was saying, you know, this is the 2 norm, this is the 1 norm, this is the infinity norm. Because a lot of times I would also adorn this with a sub p to remind myself I'm talking about the p norm. He doesn't do that, but I'm just saying you might do that. If you're going to work with more than 1 norm, you probably want a notation to distinguish which norm you're talking about. Now, he says, but we do have defaults, right? So like if you're talking about Rn, what's the default norm for Rn? So like convention, essentially. What's that? Euclidean, right? Convention. Rn is paired with Euclidean norm, which has the same formula, right? So like the norm of x is equal to the square root of x dot x. There we go. I'm gonna be lazy and use the dot product since we know about it, if that's okay. All right. Although I think technically I just jumped ahead to chapter 3 on a conceptual level, if that's okay. All right, so bringing us to the next topic, which is, well, once you have a norm, what do you do with it? You measure distance, right? And what's the thing we're looking at in part is, well, sequences. And so we're interested in describing convergence of a sequence. And so here it is. This is going to be convergence in norm space. All right, so definition, we have, and we usually write it as a pair, right? So like this notation is just, you know, just to say, hey, I'm taking this vector space, I'm pairing it with that norm, right? I'm going to say I'm going to use the NLS because, you know, less writing. then we say sequence xn of elements in E. In other words, a sequence in E, all right, converges, that's what's being defined, to some x in E, right? If for every epsilon greater than 0, and by the way, if you're teching that, it's actually variable epsilon, var epsilon. You know that? It's like this. I'm telling you this because many of my older notes have epsilon there and it looks dumb. I can't spell epsilon. I can't spell epsilon. You get the idea. There exists M he just says a number. Huh. I would usually say an n. I guess I usually say a natural number, such that for every n greater than or equal to m, we have the norm of xn minus x is less than epsilon. So at this point, having just completed real analysis, this feels very comfortable, right? Because by golly, this is just the definition of convergence of a sequence of real numbers, right? Except what's the difference? We replaced absolute value with norm. Did you do any stuff with metric spaces in real analysis class? Just enough, right? Yeah, because you can spend an hour on it and say a lot without working too much, you know? So it's good that he did that because it really doesn't take much work. And I mean, sure, some of the students have no idea what you're doing, but for the better students, it's important that you did that. It's good that you did. So, but yeah, it's so much like what we saw in real analysis. And he says the definition is simpler if convergence of real numbers is used. And I think that's a typo. Like, I think he means absolute value there. For that to be an interesting sentence, I think that norm right there under the definition is meant to be an absolute value. All of a sudden, right? Otherwise, he's just repeating himself as far as I can see. So I think that's meant to be absolute value. Anyway, the convergence in a norm space has the basic properties. So like, here's some theorems, right? So here's a theorem. If xn goes to x and lambda n goes to lambda, right? So this is, I guess I should, there's a more verbose way of writing this, but I'm just going to kind of adorn it like this. So this is in E. This right over here is in F. So in the scalars, in the vectors. All right, then what? Then if you take the product, lambda n xn, it goes to lambda x. And also if you have xn goes to x and yn goes to y, then there's the sum of the two sequences it limits to the sum of the limits. So these are limit laws without limit notation. Although it's, yeah, it is, but
You could prove it the same way, really, as in just the real rises. It's basically the same definition as sequences.
Sure. How would you prove the second one there?
Second, since given epsilon greater than n, there is to n sub 1, just that's for any n variable. To n sub 1, the norm of x of n minus x is less than epsilon over 2, and then likewise for y, you just use the triangle inequality with the norm of x of n plus y sub n minus x of n.
So how did you choose m?
Oh, that's right. Yeah, just choose. I was just gonna say the individuals converge. I was just setting up the definition for each of those.
So like, I mean, I think you can choose mx in n and my, let's say, in n for which.
Oh, sorry.
You're fine.
It's equal to, let's say, the maximum to.
Yeah. So I guess now. I guess I should just be clear. For which the norm of xn minus x is less than, what I want, and the norm of yn minus y is less than what I want, and I can make it small as I want, right?
Yeah.
So epsilon over 2. That's perfect. So you put epsilon over 2 here. Yeah. So you recognize this is the proof. This is the proof of the sum of the limits. Yeah. And then, like you just said, we take m equal to the max of mx and x, and this is just a plain old pick the biggest of two numbers to max. So.
No, I
and
know the difference. You said super more.
Oh no, the fact that you're asking the question means that you're aware of the issue. So n greater than or equal to m implies the norm of xn plus yn, and like you said, use a triangle inequality. Oops, my bad. Minus x plus y is less than or equal to. I'm probably working a homework problem right now, aren't I?
Oh, yeah. Sorry.
No, it's fine if I am. I'm just saying, I wonder if this is a homework. If it's not, it should be. And I really shouldn't have worked it because our class time is valuable. But I'm tired and I like to do.
Yeah, no, it's fine. That's the epsilon.
Okay, so all right. What about the other one? Like, how would we work that one? What do you think? Like, how does that other one go?
If it converges, then
so that proves then that that proves the linearity one, right?
Yeah.
Okay.
The product one, you have to take out one because it's series term.
Man.
That's probably homework too. Probably work it out.
So yeah, we got to. The question is, how do we bound? We've got xn lambda n xn minus lambda x, right?
Yeah.
You gotta make that thing small. But,
Add and subtract and the
okay, add and subtract what? What do you think?
y sub n, x sub n plus
What's y?
times x sub
No. We're just trying to prove. I'm interested in the scalar multiple. The item, this one here. There's no y.
Yeah. Which one?
See what I have. I mean, like you said. I mean, I get control of this, whatever you want, and I get control. I get control of this,
Yeah, you want to do epsilon.
whatever I want, right?
Yeah.
But how do I get from this to? I mean, okay, this is supposed to be that. Sorry, but I have a suspicion that this is much harder.
Okay, yeah. That's good.
See, because in the case that the vector space is the real numbers and the scalars are the real numbers, this has to reduce to the proof that the product of the limit of a product of sequences is the product of the limits.
Yeah.
And I don't think that's easy. I don't think that's an easy one.
Oh yeah, that one.
I bet he did it in class though, yeah?
Yeah, no, it's in the old textbook and stuff.
So probably you'll have to, like, whatever the trick is there, you'll have to kind of like do that here. And I think you're right. I think it's adding 0.
Yeah, you add and subtract in the norm, like.
Okay.
Which one,
Let's try it. Let's just try something. You almost can't go wrong.
sub n plus, let's do y sub n x.
There's no y though. So how about like what about this? Like minus lambda,
Lambda sub n.
like that,
Yeah.
and then
Plus lambda x sub n.
this might do. I haven't tried this before, so I'm just
Try what we call
trying something.
the lambda sub n x sub n minus lambda x sub n term.
Right.
And the norm of that. So that's like the norm of that plus the norm of lambda x sub n minus lambda x.
So like, am I doing it right? This is what you want?
Yeah, sorry. I'm sorry.
And I'm gonna skip a step if that's okay with you.
Yeah. And think of that, yeah, exactly, yeah. And then you use for the x sub n minus x as 1 over.
Oh, I can factor out the xn there. My bad. Right?
Yeah.
Dummy. Not me, not you. Let's see here. So lambda n minus lambda xn.
Yeah. And he hasn't proved yet that, or we haven't proved yet that if it converges, or if the norm converges, it's bounded.
And then we have the absolute value of lambda n minus lambda times the norm of xn
Yeah.
plus the absolute value of lambda times the norm of xn minus x. So yeah, so then what we need is the result that if the limit exists, then the sequence must be bounded.
Yes, exactly.
So if we knew that,
Yeah, we knew
like,
everything else.
yeah, once we know that, then we have the necessary.
Yeah, you get it out, and then you do the epsilon stuff.
But yeah, so that's a good place to stop on this. But
Yeah.
that's what's involved. It's not trivial. This one's not trivial.
Right, yeah. It's okay if I take a picture.
Oh, absolutely.
Sorry, yeah, I forgot to have it some that normal versus the
So, I wonder if I bet that's a homework problem, yeah?
Yes.
If it's not, then I owe you the rest of it. Here, so, I don't know. If I had my calculus notes on me, I could go look it up. Like, I used to have this proof of, because it's the same, for the epsilon delta limit, it's the same trouble.
Right, exactly.
Like the proof of the limit as x goes to a of f of x times the limit, f of x times g of x is the limit of x goes to a of f of x times the limit of x goes to a of g of x. Well, it's not a sequence problem. It's the same mathematical trouble.
Yes, yeah, same process.
And I had a proof in my notes when I just worked it out from my own just brute force. I had like a proof using like a quadratic formula kind of thing. And I don't think it probably wasn't quite right. And I looked it up on Wikipedia and I found out there's just like beautiful, sneaky argument that you can give. And now that's in my notes for my calculus better. But okay, let's go on. So example 1.3.7. So as a general rule of order in here, when I try something like this, I'll go as far as we get. Once we get to a point where we know it's technical and like, sometimes we'll just move on and yeah.
Sorry for the distraction.
No, you're fine. Uniform convergence. So this one's interesting. Uniform convergence. So again, we consider the space of continuous functions on a closed bounded subset of Rn. So C omega, where omega is a subset of Rn. Uses a capital N there. And so this guy is closed and bounded, which because of theorems that we know from multivariate analysis. So I don't know, like I feel like I'm not sure if I'm like foreshadowing theorems that are in this book, or it may be assumed in prerequisite material. Like I don't know if the closed bounded implies compact is something that's in this book. Maybe not. Did you talk about like, yeah, you talked about Heine-Borel?
Yes, I
So you-
personally will review it probably.
So you probably did the Heine-Borel in the reals, in your real,
Yeah,
right. But it continues to be true in Rn.
Oh, okay.
Yeah, yeah, yeah. So, in other words, a closed and bounded subset of Rn is a compact subset.
Thank you.
Yeah. And compact means that, for every, well, there's different notions of compactness. You can define compactness in the topological sense. You say, okay, so like every open cover of the set has a finite subcover, which, depending on the book, you may or may not have done.
Yeah, we did.
And then, yeah, that's later. But then there's also sequential compactness, where you define compactness in terms of like sequential limits, I think. So, okay, let's move on here. So, anyway, it's closed and bounded, right? So we say a sequence of functions converges uniformly to f. So then, f1, f2, f3, and so forth and so on, forever and ever, amen. Element of C omega converges uniformly. Did I pray today? I don't. I feel like I might not have. I can't remember. I'll pray twice next class. I'll make up for it. So here, so converges uniformly. If I'm in the middle of something when I'm starting class, it's anyway. Okay, so converges uniformly if for every epsilon greater than 0, there exists a constant number n sub naught such that the absolute value of f of x minus f sub n of x is less than epsilon for all x in omega, and all n greater than n naught. So let's see here. He says it's easy to see that the norm that we defined in example 1.33 defines uniform convergence. That is, a sequence converges uniformly to f if and only if. So he claims that this right here is equivalent, right? It's equivalent to saying that the norm of fn minus f equal to the max of x in omega, absolute value of fn of x minus f of x goes to 0 as n goes to infinity. So that's the reason he says that this is called the uniform convergence norm. So there's two different kind of complicated things going on at once here, right? Like the one is you're letting n going to infinity, right? But the other is that you're sorting over all possible x's in the space, So I mean, I'm trying to think of some kind of picture I can draw or something to explain this better, but the uniform convergence, right? the key aspect here that makes it uniform convergence versus the other kind of convergence is that this n naught here does not depend on x, exactly. And that's the difference between this and pointwise convergence. Yeah, in pointwise convergence, it's like f1, f2, f3, da da da. In that converge pointwise converges. I missed the end of this sentence here. Converges uniformly to f. That's kind of important. To f. My bad. To f. All right. So it pointwise converges to f if for every epsilon n greater than 0 there exists a n naught, you could say n naught of x, such that this for all x in omega. So this for all n naught down here, yeah, maybe I'm not. Let me, oh goodness, let's just write it out. So here's the pointwise convergence. This is example 1.3.8. So we have, and here he's being more specific. He's got f, f1, f2, so forth and so on in the continuous functions on the closed interval 0 to 1. By the way, that is a closed bounded set right there. Yeah. And he says the space of all continuous functions on the closed interval 0 to 1. Yeah, great. The sequence, so definition, sequence fn, pointwise converges to f, all right, if the Ep's value of fn of t minus f of t goes to 0 as n goes to infinity for all t in 0, 1, for every t in 0, 1. And I think like another way to write that, right, would just be like the limit as n goes to infinity of fn of t, right, is equal to f of t.
So the difference with pointwise then would just be that when we say that the absolute value of f sub n t minus f of t tends to 0, the natural number that we're selecting for each epsilon there, it does depend on whatever point t we're dealing
Right.
with in 0, 1.
Yeah, you can choose a different, you can choose a different n sub naught for each choice of t here. The uniform convergence forces the same n sub naught for all.
Okay.
And yeah. So like, you can start to draw a picture for this one. You can kind of like, and I think he has some of those pictures in here later. I don't know if it's close by or not. Yeah, like page 15 is the sort of kind of picture that I'm thinking about. It's got, this is page 15.
Oh, yeah.
Do I need to come closer?
Maybe just a little bit, actually, yeah. Yeah, that's good.
Okay. So page, basically that you know, so here for a given epsilon, right? If you think about the picture over here, so like, you know, you've got the graph of your function, maybe it's like this, right? Y equals f of t. I guess we're just going 0 to 1, so let me be 0, 1, right? And so if you're trying to look at, absolute value of fn of t minus f of t, let's say to be less than, just for the sake of specificity, a half. That's too much. A quarter, right? That's saying that the distance between, for a fixed t, right, like here, that value is f of t. See, so there's a band, a quarter plus or minus, along that graph that you got to think about, right? And so, like, maybe the graph of f1 is wackadoodle. Maybe f1 looks like this. Whee! But the point is, for n sufficiently large, the graph settles down. You can pick far enough out, in the case of uniform convergence, so that like eventually the graph of the sequence functions has to fit in there, right? So this is for n much greater than 1, just to be vague. For n larger than that n sub naught. But that, that has to hold for all 0 to 1. With the pointwise convergence, all you have to do is at each point to be able to go past, sufficiently far so that the function's, is close to it at that one point. But that one value of n doesn't have to work for everything. So like the pointwise convergence just looks at a point. So, yeah, and so they are different modes of convergence. They're not the same at all. And there are nice theorems for uniform convergence which are not available for pointwise convergence. I think pointwise convergence is the more sort of first order natural idea to try. But I think the point of the book and the next result is that it's actually an unnatural. I think that's what he's arguing next, in not so many words, is that it's an unnatural notion of convergence, because like the next example here, where was I? Yeah, page 11. Pointwise convergence there, right? So, where was I? Here's a good place, I guess. I guess I'm just continuing example 1.3. I didn't finish it yet, actually. Okay, so he says a claim. He doesn't say claim. I'm adding claim. Claim. There does not exist norm on the continuous functions of the closed interval 0 to 1, which defines pointwise convergence. And I have to assume he's meaning in the same sense, like I was just using example 1.37, right? Like the max norm defines uniform convergence in this sense, right? So like for a norm on C01, hypothetically to convert, to words. So let me just write it symbolically here. So like we're saying limit as n goes to infinity of fn of t equals to f of t, yes, for all t in 0 to 1, right? That symbolically is pointwise convergence. All right? And that is equivalent, he claims, is not equivalent. There does not exist a, like, you know, a norm of Fn minus F going to 0 as n goes to infinity. It says, like, it claims that there does not exist such a norm. Okay, so he says, so his proof is by contradiction. Suppose to the contrary, that there is a norm such that, you know, this goes to 0 if and only if this, all right? And then he says, consider the sequence, consider the functions gn of t, and he's got 2 to the n times t, 2 minus 2 to the n times t, and 0. And so the first one, we've got 0 less than or equal to 0 less than or equal to t less than or equal to 2 to the minus n, and then 2 to the minus n less than or equal to t less than or equal to, what is it? 2 to the 1 minus n. Okay. Else. Otherwise, yeah. So let's see here, how's that work? So, like n equals to 1, what's that? I think it's just, you know, whenever I come across something like this in an analysis book, like, you just take a second and like make a graph, like, that's what you want to do. So we're 0, we've got 1, right? Look at n equals to 1, what does g1 look like? 2t, and 2 to the minus 1 is a half, right? So we have slope 2t, we come up to the point 1. So it is a line, and then that is slope minus 2. The y-intercept is 2, so it's actually just back down like this. It's just, yeah, it's just a spike. And then, so that's g1 of t. What is, you know, what does g10 of t look like? It's something like, you know, it goes, maybe 10 is too much, 4. If I pick 4, I'm going 2 to the minus 4 is like 1/16. And I think that 1 minus 4, that's 1/8. So from 1/6, so it goes from 1/6, like it goes from the 1/16 to the 1/8. And it's yeah. What's that? N equals 4. I go to a 16th in the middle, and then 1 minus 4 is minus 3, which is 2 to the minus, yeah, it's an eighth. And so what happens here, as n goes larger and larger, the tent kind of squeezes down and down and down. Like that, like that's the nature of this example. How does that get us a contradiction? What's he say? He says, since gn is not equal to 0, we have the norm of gn is not equal to 0. All right, so we have norm of gn is not equal to 0 for all n. I agree with that. And he says, define Fn. And this same trick he uses soon later in this section. So like this is the first time we're seeing this trick, but it's not going to be the last time. What is this? This is the normalization trick, right?